It is my pleasure to give this keynote talk at IEEE ICRA. I would have loved to come to Paris and give this talk in person, but that's unfortunately not possible. I will talk today about human-centered approaches to social robotics, and I will particularly focus on autonomy, trust, and interaction challenges. I moved to Canada in 2018 as the Canada 150 Research Chair in Intelligent Robotics. I'm working at University of Waterloo in the Faculty of Engineering, but I'm also cross-appointed with the School of Computer Science and still have a joint affiliation with the University of Hertfordshire in the UK, where I worked for many years. At University of Waterloo, I'm the director of the Social and Intelligent Robotics Research Laboratory, where we focus on different themes related to human-robot interaction, social robotics, but also cognitive and developmental robotics and artificial intelligence approaches. Now, why is human-robot interaction interesting? Why do researchers work in this field? Well, we are talking about robots that are social robots, and where a key purpose of their functionality is that they are interacting with people. And robots are different from traditional interfaces that are, for example, being studied in human-computer interaction, but they're also different from robots as pure machines, for example, how they're used in industrial robotics. So there are things happening in face-to-face human-robot interaction that you cannot predict by knowing about interfaces or knowing about computers or knowing about robots such as the ones used in industry. People have different interest in this field, so they might be interested in the robots as an autonomous creature. So how is it able to operate autonomously in an environment, recharge, and so on. People might be interested in the AI aspects, for example, machine learning aspects, so the more robot cognition-centered approaches. And finally, the more human-centered approaches, which is about designing for people. And more application areas show how important it is that robots are able to interact with people in an efficient but also enjoyable manner, so that they are being trusted and are being used. So there are several definitions of social robots that we could look at. So for the moment, let's just look at the definition that we used in the recent edition of the Springer Handbook of Robotics, which characterizes social robots as being designed to interact with people in human-centric terms and to operate in human environments alongside people. And these robots can come in different shapes and sizes, but it's very important that they interact and communicate with people in an interpersonal, in a social manner, using different cues, verbal, non-verbal, but also affective modalities. Now, robots are not what they used to be. These days, for example, we have also autonomous cars, but we also have systems that are not being sold as robots, such as the ones you see here, but they clearly have abilities to perceive aspects of the environment, to make decisions, and to act on the environment, for example, to order pizza for us. But still, they are not being considered as traditional robots, but it is quite exciting to live in these times and to see what type of systems might we have in the future. And there's a whole spectrum of different social skills these robots might need, and that depends very much also on the application area. If you use robots in therapy or as home companions, so companions maybe for older people in their own homes or in hospitals or in care homes, then you're talking about very close, repeated, long-term interaction. On the other hand, in application areas where the robots are spatially or temporally separated from people, then you don't need any of such skills to an extensive degree, because after all, implemented social skills are costly. They require a lot of effort and a lot of time. So in the remainder of my talk, I will focus on robot companions, and I define robot companions as robots that have certain tasks. They have to make themselves useful, but they carry out these tasks in a way that is socially acceptable to people. Now, I now like to talk about robot autonomy for such companion robots, in particular different levels of autonomy. And I will draw on two application areas that I've been involved in over the past more than 20 years. So one is about using robots in robot-assisted therapy, where I've been involved in various projects at University of Hertfordshire, but also large-scale European projects such as iRomec, RoboSkin, or Baby Robot. So the role of the companion robot is here to support play of children with autism, interacting with the robot, addressing educational or therapeutic goals. The robot is a tool here in the hands of therapists, teachers, or also parents. And it's not a scenario where the robot interacts alone with the child. The robot is a social mediator. There's always another person involved in the interaction. And the learning for the child with autism takes place in a non-judgmental, playful, and enjoyable manner. So we're designing all scenarios, particularly having those things in mind. And there is, in fact, also a workshop together with colleagues from Belgium and France that we are organizing a workshop at ICRA specifically on social robotics for neurodevelopmental disorders. So one of the human-centered aspects in this domain is about user-centered design and redesign. So for example, the Casper robot that we developed at University of Hertfordshire has been designed and redesigned since 2005 over many generations, and based on feedback we got from the research, but in particular also input from parents, teachers, and therapists. So human-centered design is not only on the level of the software, it's not only on the level of the interfaces, but it's also in terms of the appearance of the robot. And last but not least, robustness. If you want to have robots that you can put into a school, into someone's home, into a therapy center for an extended period of time, the robot has to be robust. And in fact, with the Casper robot, we just recently got a paper accepted about a study where the robot had been used by teachers and therapists in a nursery school for children with autism for more than a year. Well, in fact, it has been used for more than 5 years, but that particular paper just focuses on the 1 year study where we regularly did interviews with the teachers in order to get their feedback on the use, the usability, and the usefulness of the robot. And we're targeting in this domain many educational and therapeutic objectives. This can be practical ones, so for example, teaching about hygiene and food. This can be educational one, teaching about communication skills, collaborative skills, or it can more address therapeutic issues such as teaching about turn-taking, joint attention, but also how to use emotional expressions in order to regulate interactions. The other area that I will draw upon is about home companion robots. So robots that are meant to assist people in their own homes. And in fact, at University of Hertfordshire, we've done many studies in our robot house, which is a smart home that also other people can use in order to carry out research into smart home and robotics technology with various types of humanoid and non-humanoid platforms and mobile manipulators. So the types of assistance here of these companion robots is a little bit different. It's more about the robot providing physical assistance, social assistance, being a coach or a personal trainer, or serving as a cognitive prosthetics, which means as a reminder. And a lot of research in, for example, many European projects has been carried out in terms of developing such systems that can embody many of those functionalities. If you just wanted one of those functionalities, for example, to remind a person to take medicine at a certain time of the day, you could also use your smartwatch. But if at the same time you would also want the robot to provide physical assistance, then you would need a robot. And these are just some illustrations of some research platforms that we've used in the past. So let us now look at different levels of autonomy that is based on my experience in these two application areas and lessons that we have learned. So the lowest level of robot autonomy is a Wizard of Oz controlled robot. meaning there is a hidden operator, hidden from the people interacting with the robot. This means, in particular, if it's a complex scenario and a complex robot, it could be a high cognitive load for the robot operator. In some scenarios, we even needed 2 or 3 of those operators. It has an advantage since these operators, they have human knowledge. They could also be domain experts in these areas, so they can trigger robot behaviors based on this expert knowledge. But it's unrealistic to actually use systems with such a control in the real world, because it would just increase the requirements of having more staff employed in very cognitively demanding tasks. And there's little added value of having a robot in such a scenario when it can in fact be people carrying out these tasks. The next level, I would say hybrid control, meaning there are some autonomous behaviors, but the overall scenario control is done via an interface. With children with autism, we've used this quite successfully, where it was actually the children often controlling the robot, which gave them a sense of ownership and to be in control of the situation. But you can, of course, also have therapists or parents being in control when they play with children. Now here the interface design is crucial. And the advantage here is that the human in the loop makes sure that the responses of the robot are adequate, suitable, and timely. So the next level, let's talk about semi-autonomous robot companions. This means that you have a number of autonomous behaviors and autonomous decision-making, but it requires the approval of a supervising adult and the ability of this adult, of this operator, to also override the robot's decisions if it turns out, for example, that the perceptual abilities of the robot did not give the result, or that the robot made a mistake in order to analyzing a particular situation and choosing an appropriate action. So this is a way how you can exploit robot autonomy and different ways in how the robot could autonomously, for example, navigate, manipulate objects, communicate with people, but you still keep the human in the loop. And that's particularly useful in applications where the robot serves as a mediator, where you anyway have a person, a nurse, an expert, a teacher present. So that person could then basically monitor what the robot is doing, and if necessary, override the robot's decisions. The next level is fully autonomous in the sense that it really relies very much on the reliability and robustness of the robot's perception and decision making. This is very, very complex, and it means that if you have very complex scenarios and application areas, often these scenarios have large elements of being pre-scripted, so they lack flexibility, and the robot might not be able to adapt on the fly. So the reason here why there are limitations is that it's very unlikely that the robot has the domain knowledge and perceptual abilities that human experts would have, that teachers for children with special needs, or that nurses and doctors have when they interact with people in care homes. So it's very challenging to develop robots that can fully autonomously operate in these tasks, in particular if they have not just one task, but they have multiple tasks and need to operate in real time. Now, the final level is autonomous and adaptive. So again, you have high levels of autonomy, but the robot is able to learn from the experience, with the goal that it could then be able to adapt to changing needs, changing requirements, possibly also learn new functionalities while it is interacting long-term with people in hospitals, in schools, in care homes, or office environments. However, it really requires on a solid model for what, when, and how to adapt the robot's responses, which is non-trivial. to decide on, and it might, depending on the approaches that you use, require large training data, which is unsuitable for many real-world applications. So let me just make another point about robots and the need that they need to provide an added value. And I'm particularly fond of scenarios where the robot can do tasks that a person could not do. So what you, for example, could do with the robot is that you can visualize that the robot can see. You can put a screen next to the robot, and then people interacting with the robot can put themselves into the shoes of the robot in order to understand what the robot can see. And we have explored this extensively in the European Baby Robot Project, in particular with regard to visual perspective taking, which is exactly about this ability to consider what someone else can see and how they see it and what they cannot see. So there are different levels of visual perspective taking, and it's particularly relevant for children with autism because they lack abilities in one of these aspects of visual perspective taking, which is called visual perspective taking level 2, which is about understanding that two or more people viewing the same object from different points might see different things. It's something that is intuitive typically when we grow up, but children with autism might have great difficulties with that. So we have developed a set, and in long-term studies in special needs schools with a number of children, we've developed different scenarios of increasing complexities. We also did some pre and post tests and evaluations of the children's abilities to understand what another person, but also what the robot can see. And we have also recently published results from these long-term studies. We also did, as part of that project, some investigations into reinforcement learning, where pairs of children collaboratively could also teach the Casper robot about a particular game. Now, another aspect I would like to make is about what should robots actually do when they are not interacting with people, because we are talking about long-term and repeated interaction. So these robots are not non-stop all the time interacting with a person. So should they just disappear? Should they just recharge? Should they stay around and just provide company to a person? And so the question is really, what should the robot do when it's not engaged in an interaction? How would people perceive it? Would they notice it? Would they say, would they judge the robot in terms of how likable or how intelligent it is? And that was a study that we did in 2015 with a non-humanoid robot, and the scenario was that the person is engaged in a task and people watch video of this person, and opposite the person is a robot, and the robot is responding to the person's activity with movements that are either contingent or not to the robot, to the person's movement. So this was the setup: the person engaged in a task, the robot observing and either moving in synchrony with the person, so we call this positive synchrony, or into the opposite direction, negative synchrony, or the robot didn't move at all. So here you see just some pictures and illustrations of this particular scenario. So we did an online study here where we had in the end over 100 usable responses, and we found that in terms of likability and perceived intelligence, that people significantly preferred the robot that shows movements contingent with the person's movements, followed by the ones that are contingent but in the opposite directions, which we called negative synchrony, and the least liked robot and the ones perceived as least intelligent was the robot that didn't move at all. And we didn't find any differences in terms of gender or people's previous experience with robots or knowledge of the particular robot that we had. We also used a scale called the iOS scale, inclusion of other in self, which was about how close people felt when they were watching the robot, how close they felt to the robot. And again, we found that positive synchrony, which was perceived as much better than negative synchrony, followed by a robot that is not moving at all. So here our initial hypotheses were confirmed. And it just shows how important it is, even with a robot that is not engaged directly in a task with a person, to think about what the robot should do. And that's in fact something we have just this year published in a journal paper together with Silvia Rossi. Now, my final point is about trust and trustworthiness of robots. Now, that has been studied extensively in human-computer interaction, but also in psychology regarding human interactions. So clearly, in terms of robot companions, they have to also be safe and trustworthy. And a lot of research over the past 10 years has been done with many research groups showing that people seem to have a great level of trust in a robot, very often over trust. So even when the robot is wrong, they might still follow the robot's suggestions, the robot's instructions. They might still trust the robot. And to illustrate this, we did a study in our robot house, where we found that even when the robot was presented faulty, when it made mistakes when they were introduced to the robot, and people perceived this distinction. They clearly found the robot, when it was faulty, they found it less trustworthy, less reliable. But when we then observed, would people follow in different types of tasks? Would they follow the robot's suggestions? The majority of people, and sometimes even 100% of people, followed what the robot suggested. So they trusted the robot, even when we had very unusual requests. But the percentage of people following the robot's request also differed depending on the tasks. So and also more recently, we have done another study where we also found that the frequency and magnitude of the robot's errors also influences the way how robots trust the robot. This was not a live interaction. It was based on storyboards where the people went through different stories and made decisions how they would interact with the robot. And in the end, we presented an emergency scenario and we measured how people would react to that. And we had different conditions depending on the magnitude of these errors and when these errors occurred. And so what we found is that the magnitude of the error correlated with the loss of trust, and also participants' personality traits had an influence on this level of trust, and also the disposition of trust in general. So how likely are they to trust, including other people? So in terms of challenges for those experiments on human-robot trust, there are, of course, many ethical issues involved. You need to study different types of tasks, different types of participants' personalities. You need to decide what type of measures do you use. Do you observe the behavior of people? Do you use questionnaires, which are more subjective, self-report measures? You also need to look at the frequency, magnitude, and criticality of the errors. And this is also very much related to the recent research fields on that are promoting explainable AI and the fact that robots' behavior has to be legible and transparent. So to conclude, a few questions now for HRI and social robotics. We have seen over the past few years that many robotics companies that were selling social robots, in particular companion robots, robots as assistants, were not successful. So robotics is hard, social robotics is even harder. And we need to consider that there's a long way from a promotional video to a robot delivering multiple functionalities and services in a complex, dynamic, and unpredictable environment. We also need to consider in application areas such as home companion robots or robot-assisted therapy for children with special needs that while many commercially available robots exist used in research, where are those robots? We have millions of potential users of these systems, but I'm not aware of millions of these systems who have been sold and who are now operating in people's homes and schools in order to help that population. So it's still a very long way for research to go and to make progress in this area. But it is ultimately necessary because we would want these robots, these social robots, these companion robots, to have a real impact in the real world. And we need to make sure that we adjust people's level of trust in order to avoid overtrust in robots. Since robots are machines, and like any machines, robots can fail and they will fail. So overtrust is a very dangerous component, and a lot of more research is needed here. And we also need to look at more closely at different levels of robot autonomy and learning and adaptation that could be desirable in many of those application areas. Thank you.